Hello, I'm Scott Yaeger, President and CEO of Filtration and Separation Technology International, FAST for short. In 2004, after spending a myriad of years as a senior level executive in the areas of engineering, research and development, manufacturing, marketing, sales, and general management, with a variety of filtration and separation companies, I started FAST, a consulting company to the filtration and separation industry. Prior to starting FAST, I was a Senior Vice President and General Manager of PTI Advanced Filtration. When I started with PTI in 1996, the total sales were $2 million. By 2000 year-end, PTI sales reached $24 million. Of the $24 million, 50% was organic growth and 50% from the acquisition of Advanced Membrane Technology, AMT. This acquisition included the development, manufacture, and sale of spiral elements, thus giving me insight into the technology, applications, strengths, and weaknesses of spiral elements. After starting FAST, I realized that the then current spiral element design did not effectively use the membrane area for high flux membranes. A spiral element design had changed very little from when they were first developed in the late 1960s for use with very low flux RO membranes. For low flux membranes, the AMT element design performed reasonably well. But for many of the newer membranes that are available for ultrafiltration and microfiltration, the spiral element worked very poorly, as effectively using as little as 5% of the available membrane area. A 3,000 liter per square meter per hour membrane, when put into a 28 square meter, 20 centimeter diameter spiral element, should produce over 1,500 liters per minute of permeate flux. This would overwhelm the 2.5 centimeter permeate tube. In reality, it typically gets about 38 liters per minute of permeate flux. This means that less than 3% of the available membrane area is being utilized. With ultrafiltration membranes, we see more membrane usage, but still only about 30% of the available membrane area. Spiral element devices are the format of choice for reverse osmosis and nanofiltration, which are low flux membranes. The spiral elements with ultrafiltration membranes are used in very few markets, such as electrical paint and dairy, but these too are relatively low flux applications. It is no wonder why these elements are not being utilized where high flux membranes are used, which is mainly in water and wastewater applications. Starting in about 2006, I was researching why this was occurring. I looked at the fluid dynamics of a spiral element and discovered the problem. It was a driving force, the pressure pushing the fluid through the membrane, which was being measured at an inappropriate location. When measuring the feed and the concentrate pressures, they are relatively accurate, but in measuring the permeate pressure away from the membrane, where it has the greatest effect on the permeate rate, the effective pressure is inaccurate. There are many opportunities for the permeate flow to be restricted. There are at least 4 areas identified within the spiral element. These areas are from minor to major permeate flow restriction, and thus there are high permeate pressure at the membrane interface. Our new element design eliminates those flow restrictions. Some of these design changes can adversely affect the cost of manufacture. This could limit one of the strengths of the spiral element, its low cost per square meter. FAST has overcome this issue by patented spiral design that incorporates all the flux-resistant minimizations, but still keeps the manufacturing cost at or below that of a spiral element. Standard spiral element. This was the subject of the first patent applied for in 2008 and granted in 2013. The patent is for a fully welded spiral element. In 2009, FAST built a prototype shop in our new facility and hired Eric Yaeger to implement the patent into a viable spiral element. Eric is the lead for the FAST team in the development of the assembly technology and prototype element builds. The FAST team has built a wide variety of small prototype spiral elements that incorporates the flux-resistant minimization design. These prototypes have resulted in flux improvements of 5 to 10 times that of a standard element, utilizing the same ultrafiltration or microfiltration membrane. As you can see from the graph, a standard microfiltration element, spiral element, is providing about 100 gallons per square foot per day at 25 psi transmembrane pressure. That is the bottom line on this graph. Our first modification of the spiral element with the same membrane is resulted in Gen 1. In Gen 1, we have 650 gallons per square foot per day or 6.5 times that of a standard spiral element. We then further removed some flow restrictions, and we ended up with Gen 2, which is at about 9.5 times that of the standard spiral element at about 950 gallons per square foot per day. The fast spiral element is effectively using 100% of the available area for ultrafiltration membranes and 50% of the microfiltration membrane. Trials with the fast elements in the laboratory and the field, filtering heavily contaminated oily water containing high total suspended solids, effectively remove close to 100% of the oil and suspended solids at flux improvements near that of what we achieved with clean water, which is exhibited in this graph. The one problem we noted after 4 weeks of continuous filtering operations was that the elements were fouling more quickly than a standard element due to the loss of tangential flow velocity because of high permeate rates. While high flux rates greatly reduce the capital cost by up to 5 times, the increased fouling potential will increase the operating cost due to more frequent cleaning and element replacement. This has led to a new addition to the FAST technology with the filing of a U.S. patent on December 15, 2016. The tangential membrane cleaning velocity is kept constant from the feed end to the concentrate end. This will greatly reduce the previously experienced fouling potential and significantly decrease the operating cost. That changes were to minimize the flux resistance and provide a better path of cleaning on both sides, in both the tangential and reverse flow. The combination of these two technologies extends the time between cleaning as well as improves the elements of cleanability. So what we have here is a slide that we show a standard element in the dark blue that decreases from about 6.5 or a little under 7 feet per second to about a little over 6 feet per second from the feed end, which is at 1, to the concentrate end, which is towards the 37 at the bottom of the graph. This decrease will cause some fouling, but will give you a long operational life. As we increase the permeate rate, as in Gen 1, the orange line, the rates went from over 7 feet per second down to 5 feet per second from the feed end to the concentrate end. This increase in the drop in velocity will cause greater fouling. And then if we increase the velocity again, or increase the permeate rate again, as in Gen 2, the red line, we go from over 7 to about 4.5 feet per second, again increasing the fouling potential because of the higher permeate rate. But when we add our new technology with the stabilized flow, we take and have the same velocity at the feed end to the concentrate end, even though our permeate rates are the same as the Gen 2. So we have managed to keep the velocities high that will reduce the fouling potential, and that incorporated with the design of the first patent that we received, which provides better access to cleanability of the membrane, will improve its performance. Another advantage of the patent spiral element design is its ability for construction with materials that are more chemically and thermally compatible than that of a standard spiral element. The FAST team has built an all-fluoropolymer spiral element using a non-supported Teflon membrane and fluoropolymer components. This all-fluoropolymer element was in a field trial for 3 months of continuous operation, filtering concentrated sodium hydroxide at 90 degrees C without any mechanical failure of materials, construction, or the assembly. FAST has also built elements with less expensive construction materials, allowing for more aggressive cleaning chemicals and at higher temperatures than standard spiral elements can withstand. The previous described FAST technology has tremendous potential advantage for many current and developing applications. FAST is a small, innovative company with technologies that can be focused on particular applications that best potentially fit, that provide significant added value with limited barriers to entry, and there are no dominant technological solutions. The FAST team's efforts are focused on industrial, wastewater, recycling, and reuse. One of the industrial markets that FAST currently serves on a worldwide basis is the automotive assembly plants with the FAST electrical element. There are tremendous potential applications within the automotive assembly plants that use millions of gallons of water too contaminated for reuse. FAST is running trials at 2 of the world's largest automotive companies in the U.S. The water samples have been provided from the final rinse of vehicles after the electrical process. FAST has been able to treat each of these wastewaters with tangential flow microfiltration using the FAST spiral element, with a permeate quality equal to that of the city water currently being used for the RO system. As you can see from this picture, the feed on the left is about a 1,000 NTU turbidity, and we concentrated that by a factor of 20 times from the dirtiest of all the plants that we sampled, which was a truck plant, so that we recovered about 95% of the dirty water into clean water, and whether it was at 1,000 NTU or the 20 times concentration, the permeate water quality was the same as can be seen on the right of this slide. Another aspect of how clean this water needed to be, we had to check its organic content. And here we have an FTIR analysis, a Fourier transition infrared spectroscopy analysis that detects inorganic or carbon-based materials. And you can see that the graph on the top, which is the permeate from the MF system, and the graph on the bottom, which is straight DI water, have an identical shape. That means there is no other materials, organic materials, in the permeate water that is in DI water, which is cleaner than the city water currently feeding the RO system. This one application within an assembly plant could reduce the water consumption and waste treatment by approximately 15 million gallons per year per paint plant. And there's often as many as 3 paint plants within an assembly plant. On May 10th, FAST will be conducting a small-scale field trial at a 4th assembly plant. This trial is not only to confirm the FAST laboratory results, but also test waste from other processes within the plant, proving FAST treatment technology can result in its reuse in various locations within the facility. It is anticipated that the initial system design should be sold at less than $100,000 and have a return on investment of less than a year. This will go a long way to meet the automotive company's goal for sustainability. FAST has a strong presence in the automotive assembly plants in the U.S., Mexico, Korea, China, Thailand, Malaysia, Indonesia, and India. FAST anticipates this application of our technology will be quickly transferable to those geographical areas. They are all trying to reduce water consumption and the waste treatment in some very water-challenged areas. FAST anticipates an excellent performance fit for a wide variety of wastewater treatment applications. The FAST technology has superb performance advantage with high flux, high velocity stabilization. The FAST element will perform well in highly variable and challenging industrial wastewater. The FAST technology can be applied as a standalone technology, providing permeate water quality consistent with that of ultrafiltered or microfiltered water. FAST technology can be used as a pretreatment to nanofiltration or reverse osmosis. Industrial wastewater can be highly variable water quality and can change frequently. The application of the FAST technology will stabilize the feed water quality to the reverse osmosis systems, extending the life and maximizing their flux and recovery rates. FAST has received a follow-on patent to modify the welded spiral element by creating balanced tangential flow on both sides of the membranes. This is an adaptation of a spiral element for membrane distillation, osmotic membrane distillation, forward osmosis, or pervaporation. The first sale of a FAST spiral element, patented spiral element, was for membrane distillation to concentrate completion fluid used in the oil and gas industry. As you can see in this photograph, in the center bottom is the spiral element. We are feeding the spiral element with a highly contaminated, high total dissolved solids fluid, water, and then passing compressed air on the other side of the membrane. That compressed air is pulling the water vapor that has come across the membrane out of the contaminated liquid and creating that steam-like material that comes out of the top. It is in fact not steam because the water is not being heated to a temperature that would boil and create steam. Now, there it is, I'm sorry. If you take a look at these graphs, this is the graph on the left is a extrapolation of the results of those studies, where membrane distillation, the red line, concentrated the completion fluid from 12 pounds per gallon up to 18.5 pounds per gallon in 157 minutes. While we did the same fluid with just an evaporation technique, where we concentrated it from about 13.5 pounds per gallon up to about 16.5 pounds per gallon, it took 212 minutes using standard evaporation. And the part of the side of the right, you can see that membrane distillation resulted in 1,128 grams per hour of concentration with an average temperature of 65.6 degrees C, while evaporation only provided 386.8 grams per hour at an average temperature of 111.1 degrees C. That translates to 3 times the concentration rate with membrane distillation versus evaporation at half of the temperature or energy consumed. For more information on these previously mentioned trials are in the PowerPoint presentation contained within the application of InnoStar's competition. FAST has spent the last 7 years overcoming many of the obstacles and mitigating most of the risks of implementing our patent and patent-pending technologies. FAST is seeking investments to increase the speed to market, expand manufacturing capability, address new applications in the industrial wastewater market, develop new partnerships, and assess more geographical markets, particularly in China. Thank you for your consideration of the FAST application. Sincerely, the FAST team.